So we'll now think about the extreme value theorem, which we'll see is a bit of common sense. But in all of these theorems, it's always fun to think about the edge cases. Why is it laid out the way it is? And that might give us a little bit of more of intuition about it. So the extreme value theorem says if we have some function that is continuous over a closed interval, let's say the closed interval is from a to b, and when we say a closed interval, that means we include the endpoints a and b, that's why we have these brackets here instead of parentheses, then there will be an absolute maximum value for f and an absolute minimum value for f. So then that means there exists, this is a symbol for the logical symbol for there exists an absolute maximum value of f over interval and absolute minimum value of f over the interval. So let's think about that a little bit, and this probably is pretty intuitive for you. You're probably saying, well, why do they even have to just write a theorem here, and why do we even have to have this continuity there? And we'll see in a second why the continuity actually matters. So this is my x-axis, that's my y-axis, and let's draw the interval. So the interval's from a to b. So let's say that this is a, and this is b right over here. Let's say that this right over here is f of a. So that is f of a. And let's say this right over here is f of b. So this value right over here is f of b. And let's say the function does something like this. Let's say the function does something like this over the interval. And I'm just drawing something somewhat arbitrary right over here. So I've drawn a continuous function. I really didn't have to pick up my pen as I drew this right over here. And so you can see, at least the way this continuous function that I've drawn, it's clear that there's an absolute maximum and absolute minimum point over this interval. The absolute minimum point, what seems like we hit it right over here when x is, let's say this is x is c, and this is f of c, right over there. And it looks like we hit our absolute maximum point over the interval right over there when x is, let's say that this is x is equal to d, and this right over here is f of d. This right over here is f of d. So another way to say this statement right over here, if f is continuous over the interval, we could say there exists a c and d that are in the interval, so they're members of this set that are in the interval such that, and I'm just using the logical notation here, such that f of c is less than or equal to f of x, which is less than or equal to f of d for all x in the interval. For all x in the interval. Just like that. So in this case, they're saying, look, we hit our minimum value when x is equal to c. That's that right over here. Our maximum value when f is equal to d. And for all the other x's in the interval, we are between those two values.
All this conversation around graphs, the shapes of graphs, when the derivative equals 0 to find key points, has a very important application, and that is in what we call the applied optimization problems. So our question that we're going to attempt to answer is, how do we optimize or find the most efficient, the fastest, the biggest, the smallest. How do we optimize a value of interest? And ultimately, what we're really asking is, when does the derivative equal 0? Because that's the peak or the valley. That's the optimal point for the most efficient or most profit or least expense or shortest distance or shortest time that we're trying to get after. So let's take a look at a few of these classic optimization problems, and then from there you should be able to solve lots of different types of optimization problems. The first classic problem is what we call the rectangle problem, where we're generally trying to either minimize the perimeter, maximize the area, something related to that effect. So let's say a farmer has 80 feet of fencing to enclose a pasture along a rock wall. What that means is he only has to actually fence 3 sides of the wall, not all 4 sides of the wall. So what dimensions would maximize the area? So let's draw a picture to kind of see what's going on. We've got this rock wall already, and what this farmer's going to do is he's going to make a fence that goes alongside that rock wall. So he's really only fencing 3 sides. And we need to give variables to the sides as we calculate the area, because that's what we want to maximize. So we'll say it's an x by y fence, which means the other side's also x, if we're thinking about perimeter. And we know that the area of any rectangle is equal to the length times the width, or in this case, x times the y. But that gives us 2 variables, so we need to constrain one of those variables so that we can reduce it down to 1 variable. And that's going to come from the limit we're given, is that we have 80 feet of fencing available to us. Well, if there's 80 feet available to us, that means the total distance, x plus y plus x, or 2x plus y, that total distance has to equal the 80 feet of fencing. Well, the easiest variable to solve for here would probably be y, so we'll subtract 2x, and we'll say that y is equal to 80 minus 2x, and we'll replace the y in our area formula to be 80 minus the 2x. To make life easier, we'll go ahead and distribute, so area is equal to 80x minus 2x squared. And we want to maximize this area. So if we think about maybe the graph of the area is going to increase to a certain point and then come down after that point. We're looking to find that maximum point, and we know at that point the slope of the derivative is equal to 0. So let's find the derivative of the area in terms of x. The derivative of the area is equal to 80 minus 4x. And we just need to make that equal to 0 to find the critical point where this fence area is optimized. Add the 4x to both sides, and 80 equals 4x. Divide both sides by 4, and x is equal to 20. Now that we know where that maximum occurs, we plug that in for x in the y equals equation. Y equals 80 minus 2 times 20, or 80 minus 40, which is 40. So for the farmer to maximize the area of his 3-sided fence along the rock wall, he should do a 20-foot by 40-foot fence.